Tiger sharks are among the most adaptable apex predators on the planet, capable of crossing entire ocean basins, diving hundreds of meters below the surface, tolerating pressure shifts that would crush lesser animals, and feeding on an almost absurd variety of prey, from sea turtles to seabirds to carrion, drifting in the open sea. They are not fragile specialists. They are generalists engineered by evolution to exploit opportunity wherever it appears. And yet, across different oceans, in completely separate regions of the world, tagged tiger sharks reveal the same unsettling pattern. They descend and approach a specific depth range, and then, without chasing prey, without being threatened, without reaching a physical limit, they turn upward, again and again. This depth is not random. It forms a boundary, a vertical line in the ocean that these powerful predators rarely cross for more than brief moments. It is not the deepest part of the sea. It is not near the crushing pressures of the abyss. It exists much higher, in a layer that should, at least in theory, still be accessible. So what stops them? At first glance, there are obvious explanations. Perhaps the temperature drops too quickly, perhaps prey becomes scarce, perhaps pressure begins to strain their physiology. Each of these sounds reasonable. Each would make sense. Except tiger sharks are built to handle cold gradients. They are built to endure depth. And in many of these regions, prey is still present below that invisible ceiling, which means the answer is not mechanical, it is chemical. There is a vast region of the ocean stretching across major basins of the Pacific, Atlantic, and Indian Oceans, where oxygen levels fall so dramatically that the rules of dominance begin to collapse. This is not a trench or a cave. It is a layer suspended in open water, sometimes only a few hundred meters down, where survival stops being about strength and becomes a calculation of energy efficiency. In this episode, we are going to uncover why this layer forms, why even apex predators cannot operate within it for long, and how certain organisms have evolved to thrive in conditions that push others to their physiological limits. Because in the open ocean, power does not belong to the largest hunter. It belongs to whatever can survive when oxygen disappears. If oxygen is the hidden factor shaping this boundary, then the real question is not simply why tiger sharks turn away, but how an ocean that seems so vast and life-filled can contain regions where something as fundamental as breathable water becomes scarce in the first place. At the surface, everything suggests abundance. Wind-driven currents stir the upper layers. Sunlight penetrates the first hundreds of meters, and microscopic phytoplankton perform photosynthesis on a massive scale, releasing oxygen into the surrounding water while forming the energetic foundation of the entire marine food web. In this illuminated zone, predators can hunt aggressively because every burst of speed, every sustained patrol, every chase is supported by a steady supply of dissolved oxygen. However, as depth increases, the system begins to shift in ways that are not immediately visible from above. Sunlight weakens gradually until it disappears, and once photosynthesis stops, oxygen is no longer being produced. It is only being consumed. What continues to descend from the surface is a constant rain of organic material. Fragments of dead plankton, microscopic waste particles, and biological debris that drift downward like an invisible snowfall. This material becomes fuel for microbial communities living deeper in the water column. And as bacteria break it down through respiration, they steadily draw oxygen out of the surrounding water. In certain parts of the world, particularly where ocean circulation is sluggish and deep waters are not frequently replenished with oxygen-rich surface water, this consumption begins to outpace renewal. Over time, a distinct layer forms in midwater, often a few hundred meters below the surface, where oxygen concentrations fall dramatically. Not necessarily to absolute zero, but low enough to create intense physiological stress for large active animals. Oceanographers refer to these vast regions as oxygen minimum zones, and they stretch across major portions of the Pacific, Atlantic, and Indian Oceans. This is the depth range where tiger sharks hesitate. There is no physical barrier marking its start, no visible curtain dividing safe water from hostile water. Instead, there is a gradual chemical decline that subtly shifts the cost of movement. For a predator that depends on continuous swimming to ventilate its gills and sustain its metabolism, reduced oxygen transforms every motion into a higher risk expenditure. The deeper they go, the more energy each movement requires relative to what the environment can supply. And yet, despite these constraints, life does persist inside these zones, which raises a far more unsettling question. If large predators are limited by oxygen scarcity, what kinds of organisms have evolved to endure where efficiency becomes the only currency that matters? If you like discovering how the predators really live and what actually controls its life down there, subscribe to this channel. We always post new deep-sea episodes, and the next one might change the way you see completely. What makes this zone truly dangerous is not that it instantly kills large animals, but that it slowly strips away their advantage, turning strength into a liability, and forcing even the most capable predators to operate on borrowed time. When a tiger shark descends toward an oxygen minimum zone, its body does not immediately shut down because these animals are powerful, resilient, and capable of tolerating short-term stress. The problem begins at the metabolic level. Sharks rely on oxygen to fuel continuous movement, and movement is not optional for many species. Water must pass over their gills, so oxygen can diffuse into their bloodstream, and that process depends on forward motion. The lower the oxygen concentration in the surrounding water, the harder their bodies must work to extract enough of it to sustain muscle activity. As oxygen levels drop, the shark faces an invisible calculation. Every tailbeat costs energy. Every adjustment in depth increases demand. At the same time, the water is offering less and less in return. Muscles begin operating closer to their physiological limits, and recovery from bursts of speed takes longer. A chase that would be routine in well-oxygenated water becomes far more expensive in this depleted layer. Scientists tracking large predators have observed that dives into low oxygen zones tend to be brief and controlled. Sharks descend, remain for a short period, and then return to layers where oxygen is more available. It is not fear that drives this behavior, and it is not confusion. It is constraint. The environment is setting a timer. Smaller fish, squid, and specialized species move through or even reside within low oxygen layers, effectively using them as a refuge. For them, reduced oxygen can serve as protection, because many large predators cannot sustain the effort required to hunt efficiently under those conditions. This creates a vertical barrier in the open ocean, not defined by rock or reef, but by chemistry. Above it, apex predators dominate through speed and endurance. Inside it, survival shifts toward organisms that can tolerate hypoxia, reduce their metabolism, or extract oxygen with far greater efficiency. In other words, the rules change, and when the rules change, dominance changes with them. Inside these oxygen-poor layers, survival depends on a completely different strategy, because the traits that define dominance near the surface, such as speed, aggression, and constant movement, become expensive liabilities in water where every breath delivers less return. The species that remain here are not necessarily stronger, but they are more efficient. Many fish that inhabit oxygen minimum zones have larger gill surface areas relative to their body size, allowing them to extract more oxygen from each pass of water. Some reduce their activity to the bare minimum, conserving energy by drifting rather than swimming continuously. Others possess blood chemistry adapted to bind oxygen more effectively, squeezing value out of concentrations that would push larger predators into stress. Certain squid and mesopelagic fish migrate vertically with remarkable precision, spending daylight hours within low oxygen layers where predators struggle to follow, then rising toward richer surface waters at night to feed. This daily migration is not random movement, it is strategic timing. By exploiting a layer that limits pursuit, these animals reduce the risk of being hunted, effectively turning a hostile environment into a shield. On a larger scale, entire ecosystems begin to compress vertically around these zones. In regions where oxygen minimum layers expand upward, habitable space narrows. Predators are squeezed closer to the surface, prey distributions shift, and competition intensifies in the remaining oxygen-rich layers. The result is not a dramatic extinction event, but a subtle restructuring of where life can exist and how it interacts. For tiger sharks and other large hunters, this means their hunting grounds become constrained. They are forced to patrol narrower vertical ranges, adjusting routes and dive patterns to avoid prolonged exposure to oxygen stress. In areas where these zones are expanding due to warming oceans and changing circulation patterns, the compression becomes even more pronounced, altering food webs that have operated in relative balance for thousands of years. And the most unsettling part is that these oxygen minimum zones are not fixed in place. In many regions they are growing, slowly rising and intensifying, which raises a difficult question about the future of large marine predators. If the safe layers continue to shrink, what happens to animals that depend on space, speed, and oxygen to survive? When we look at the ocean from above, it seems limitless, an enormous three-dimensional space where large predators can roam freely. But once oxygen begins to disappear, that apparent freedom collapses into something far more restricted and unforgiving. Tiger sharks do not avoid these zones because they are weak. They avoid them because the math no longer works in their favor. A body built for power is also a body built for high oxygen demand, and in water where oxygen drops below critical thresholds, even brief exposure begins to interfere with performance. Reaction times slow, endurance declines, recovery becomes harder. The predator is still dangerous, but its margin for error shrinks dramatically. Meanwhile, smaller organisms that evolved under chronic low oxygen stress operate with entirely different tolerances. Some species can suppress their metabolism to levels that would be unsustainable for large active hunters. Others possess hemoglobin with higher oxygen affinity, allowing them to extract usable oxygen at concentrations that push sharks toward physiological limits. A few microbes do not rely on oxygen at all, using alternative chemical pathways to generate energy in near anoxic conditions. In this layer, size stops being the advantage it is near the surface. Efficiency becomes the dominant currency. The oxygen minimum zone does not need to attack a predator to defeat it. It simply alters the balance of energy. If every movement costs more oxygen than the environment can reliably provide, the predator must retreat or risk collapse. Over evolutionary time, this creates a vertical sorting system in the ocean, one based not on teeth or speed, but on biochemical tolerance. And this is where the hierarchy flips. The animals that dominate coral reefs or coastal shelves cannot impose their will everywhere. In these midwater zones, power is defined by who can function under constraint. The giants patrol the boundary, dipping into it cautiously, timing their dives, managing their exposure. Below them, within the dim, oxygen-poor water, smaller and highly specialized species persist in relative safety. The ocean's deadliest zone is not deadly because it is violent. It is deadly because it removes options. Thank you for watching and spending this time exploring the ocean with us. If you enjoy understanding how these hidden systems shape life beneath the surface, consider subscribing so you don't miss the next deep sea episode, and I'll see you in the next video.